Welcome to Science Sphere. Today, we're diving into the fascinating world of sonic booms and breaking the sound barrier. What is the sound barrier? The sound barrier refers to the sudden increase in aerodynamic drag and other effects experienced by an object when it approaches the speed of sound. This speed, known as Mach 1, varies depending on atmospheric conditions, but is roughly 343 meters per second 1-3.5 kilometers per hour, or 767 miles per hour at sea level. The science behind the sound barrier: when an object moves through the air, it creates pressure waves in front of it and behind it. As the object's speed increases, these waves compress. When it reaches the speed of sound, the waves merge into a single shock wave, causing a dramatic rise in aerodynamic drag. This phenomenon was initially considered a barrier because early aircraft experienced significant challenges when approaching these speeds, breaking the sound barrier. The first successful attempt to break the sound barrier was made by Chuck Yeager on October 14, 1947. Piloting the Bell X-1, Yeager reached a speed of Mach 1.06 at an altitude of 45,000 feet, creating history and proving that controlled supersonic flight was possible. What is a sonic boom? A sonic boom is the loud sound associated with the shock waves created when an object travels through the air faster than the speed of sound. These shock waves generate enormous amounts of sound energy, sounding much like an explosion. The sonic boom is not a one-time event, but continues along the flight path as long as the object is traveling at supersonic speeds. Examples of supersonic aircraft: Bell X-1, the first aircraft to break the sound barrier, piloted by Chuck Yeager in 1947. Concorde, a British-French turbojet-powered supersonic passenger airliner that operated from 1976 until 2003, capable of speeds over Mach 2. Lockheed Senior 71 Blackbird, a long-range, advanced, strategic reconnaissance aircraft that could fly at speeds over Mach 3, used by the United States Air Force. North American X-15, a rocket-powered aircraft that set speed and altitude records in the 1960s, reaching speeds of Mach 6.72. Sukhoi Su-27, a Soviet-origin fighter aircraft capable of speeds exceeding Mach 2.35. F-22 Raptor, a modern American fighter aircraft with the ability to supercruise or fly at supersonic speeds without using afterburners. Effects and implications: noise pollution. Sonic booms can be disruptive, causing noise pollution over large areas. This has led to restrictions on supersonic flight over populated regions. Structural impact. The pressure change can cause structural damage to buildings and the environment. Historically, this has limited the use of supersonic aircraft. Aerospace advancements. Understanding and overcoming the sound barrier has led to significant advancements in aerospace technology, influencing both military and commercial aviation. Modern supersonic travel. Today, advancements in technology have reduced some of the challenges associated with supersonic flight. The development of new materials and aerodynamic designs has made it possible for modern aircraft to travel at supersonic speeds with improved safety and efficiency. However, the challenge of sonic booms remains a significant hurdle for commercial applications. Future prospects. Researchers and engineers are working on innovative solutions to minimize the impact of sonic booms. Projects like NASA's X-59 Quest aim to create a quiet supersonic aircraft, potentially revolutionizing commercial air travel by reducing the noise of sonic booms to a more acceptable level. Conclusion. The journey of breaking the sound barrier and understanding sonic booms has been a thrilling chapter in the history of aviation. It has pushed the boundaries of technology and human ingenuity, opening up new possibilities for the future of air travel. Thank you for watching Science Sphere. Stay curious and keep exploring the wonders of science.